Hi, my name is Kegan Premuda. In this video, I'll discuss the physics behind shaking ketchup out of a ketchup bottle. This motion involves the principles behind the conservation of momentum while impulsive forces are acting on the system. We have all had the same experience having your ketchup stuck at the bottom of a ketchup bottle. It seems like the consensus for the solution for breaking the ketchup free and bringing it towards the lid of the ketchup bottle is to give the bottle a few hard shakes or sudden forces that force the ketchup forward. We will begin to study this motion with an inverted ketchup bottle. The positive Y direction will be towards the ground and the negative Y direction upward. The person holding the bottle winds up cocking the bottle backwards in the negative Y direction, then applies a pushing force forward on the ketchup bottle in the positive Y direction toward the ground. The pushing force from the person holding the bottle and the gravitational force acting on the bottle both cause the ketchup bottle to accelerate downwards. The pushing force in this case is an impulsive force because it applies a force over a short period of time, which in return changes the momentum in the positive Y direction. This can be described with the equation J, the impulse equals the change in momentum equals the force over a period of time. Since the force is a vector, the impulse and momentum are also vectors. The change in momentum is the change in velocity of a particular mass, so momentum is a vector quantity that can be described by the equation the change in momentum equals the mass times the change in velocity. The velocity of the ketchup bottle is now increasing in the positive Y direction because of the initial impulsive force and the gravitational force accelerating it downward. The person holding the bottle has reached the downward end of the motion and instantaneously applies an impulsive pulling force upward in the negative Y direction, either bringing the person's hand in the ketchup bottle to a complete halt or having some backlash in the negative Y direction. For the sake of this demonstration, we will assume that the motion of the hand in the bottle was completely stopped, and the velocity of the bottle and the person's hand were brought to zero instantaneously by the impulsive force upward. At this moment, the principles behind the conservation of momentum come into play and can be described by the equation the initial momentum equals the final momentum, or it can be expanded to m1v1 initial plus m2v2 initial equals m1v1 final plus m2v2 final. Before the impulsive force that stopped the downward motion of the bottle of ketchup was applied, the momentum of the ketchup bottle system was between the ketchup and the bottle the ketchup was contained in. Once the impulsive force was applied, and since the pushing and pulling force from the hand is in direct contact with the bottle, the momentum of the hand and bottle goes to zero, and the momentum that was in the hand and bottle is transferred to the ketchup inside the bottle. We can observe this conservation of momentum phenomena because the system is isolated between the internal forces of the pushing and pulling of the hand, the gravitational force of the hand and ketchup bottle, and other internal forces between particles. Since the final velocity of the hand and the bottle are zero, the momentum of the hand and bottle are also zero, and all the momentum is in the ketchup solids. We can write a more specific equation for the conservation of momentum of this system. m1 plus m2 plus m3 times the initial velocity equals m1, the mass of the ketchup solids, times the final velocity. This transfer of momentum causes the ketchup to keep its velocity in the positive Y direction, and it experiences impulsive forces that lets it break free from the forces holding the ketchup in place inside of the bottle. The application of the conservation of momentum can be observed through other areas of life, such as firing a gun, hitting a baseball with a bat, and launching a rocket. Before firing a gun, the system is at rest, so the momentum is zero. When the bullet is fired, it moves forward and the gun recoils backwards. The mass of the gun is much larger than the bullet, so its velocity in the opposite direction is much smaller than the bullet's. Hitting a baseball involves the baseball to be pitched towards a bat swinging the opposite direction to cause an impulsive force. The momentum of the ball and the bat are conserved when the ball and bat meet, although the ball's direction changes. The hot gases produced by burning fuel inside of a rocket rush out with a large amount of momentum. The rocket itself receives an equal and opposite momentum, propelling the rocket upward with a high velocity. All of these systems involve an impulsive force that changes the direction of momentum of the objects in the system. Since these systems are for the most part isolated, then the momentum is conserved and the magnitude and direction of the object's velocity will change with respect to the mass of the objects in the system. Thank you for watching, and thank you for a great physics lab course.